Good morning, students. So today we shall be discussing the concept inflection point. That is, in the previous videos, we have been discussing the optimization of multivariable functions, and we have seen that three conditions have to be satisfied. That is, the first order partial derivatives of the function with respect to each of the independent variables must be equal to 0. And the second condition is that the second order direct partial derivatives with respect to each of the independent variables, it must be less than 0 if the function is to be maximized, and it must be greater than 0 if the function is to be at its relative minimum. Now there is also a third condition which states that dou squared is z by dou x squared into dou squared is z by dou y squared. It must be greater than dou squared is z by dou y dou x into dou squared is z by dou x dou y. This is the third condition that must be satisfied in order to ensure that the multivariable function is at its relative maximum or at its relative minimum. Now, if this condition is violated, instead of this greater than, it becomes less than. In that case, we are violating the third condition. So, which means that you cannot state with certainty that the function is at its relative maximum or at its relative minimum. Now, if this happens to be less than, instead of greater than, if this happens to be less than, in that case, there is either a saddle point or an inflection point. And we have already examined saddle point, and where we have seen that if there is a saddle point, these two would be having different signs. That is, if dou squared is z by dou x squared is, if it is positive, in that case dou squared is z by dou y squared would be negative, or vice versa. It can be vice versa also. Now, coming to the inflection point, when we discuss the inflection point, what we observe here is that here also, that is we have the violation of the third condition. The third condition is violated. It is dou squared is z by dou x squared into dou squared is z by dou y squared. It would be less than dou squared is z by dou y dou x into dou squared is z by dou x dou y. Of course, the third condition would be violated. But unlike the saddle point, what we can observe in the case of an inflection point is that these two would be having the same signs. That is, if dou squared is z by dou x squared is positive, in that case dou squared is z by dou y squared also would be positive. Similarly, if dou squared is z by dou x squared is negative, in that case dou squared is z by dou y squared will also be negative. So we are actually using this three-dimensional graph to explain inflection point. Of course, we have z-axis, we have x-axis, and we have y-axis. We are taking the point P. P is actually the inflection point that we are considering here. Of course, we are dropping a perpendicular down, and fruit of the perpendicular reads that the value of x is x0 and the value of y is y0. And of course, we know that an inflection point is that point at which the curvature of the curve would be changing. That is, the curve would be changing its curvature either from concavity to convexity or vice versa. Now, let us consider this three-dimensional graph. At point P, we have x is equal to x0, y is equal to y0. And of course, we know that P is actually the meeting point of these two curves. Here we have got two curves. Curve x0, let us say x0c, and let's have another curve y0b. Let us say that we have two different curves, and these curves are meeting at point B. So at point B, let's say what happens is there a change in curvature. Of course, it is very obvious that as you consider the movement from y0, that is, as you consider movement along this curve y0b, that is, this is the curve y0b. As you're considering the movement along the curve y0b, suppose you're moving from point P to point B. In that case, it is very clear that it is the value of x that is getting altered, isn't it? At this value, that is when you drop a perpendicular from B down, we can observe that the value of x is altered. It is x0 dash, and the value of y is constant at y0. Now, when you look at the slope, what is happening to the slope, or when you take the second derivative of the function, second order partial derivative with respect to x, of course, it is clear that it is actually rising. It is greater than 0, isn't it? So, from this, when you observe that, we can see there is actually an alteration in the curvature of the function. That is actually here we have a concave function to the left of P, and when you look at the curve to the right of the P, it has now becomes convex. Now, so here we can say that P is an inflection point. This is because as you move, that is from P to the right of P, we can see that the curve has transformed from being concave to convex. That is, at this to the left of P, you have concavity. To the right of P, you have convexity. And when you take the second order partial derivative of the function with respect to x, of course, it is greater than 0. So we can actually say that the function would be basically rising. That is to the left of P and to the right of P. On both the sides of P, we can see that the function is having a positive slope. That is actually if it had had been at its relative maximum, that is, it was actually rising at till point P and it would have actually fallen, but it doesn't fall in this case. It is continuing to rise, indicating that this is an inflection point. Similarly, when you consider the movement along this curve x0c, that is, if you are moving from point P to point C, of course, here we can say that it is because of the changes in y rather than x is constant at x0. But if you are at point C, when you that is look at the perpendicular, foot of the perpendicular, of course, it is the value of y is getting altered. It is y0 dash and x is constant. So basically, you are taking the second order direct partial derivative of the function with respect to y. Now it is also greater than 0. That is, earlier we have seen that dou squared is z by dou x squared, it was greater than 0. Now when you take the dou squared is z by dou y squared, that is also greater than 0, because when y alone changes, when you observe what is happening to dou z by dou y as you move from P to C, it is also greater than 0. So as we have observed here, the third condition is violated, and not just that, these two would be having identical signs. That is, here when you move along this curve y0b, that is from P to the right of P, we can see that dou squared z by dou x squared is greater than 0. Similarly, as you are moving from x0 along x0c from P to the right of P, we can observe that dou squared z by dou y squared is greater than 0. So they are having the same signs, isn't it? It is positive. This is also positive. And here also we can observe that there is a change in curvature. Here we have concavity, and to the right of P we have convexity. So there is a change from concavity to convexity. Now this can be further proved that by drawing the tangent lines, that is, when you consider the curve y0b, when you are drawing the tangent line, that is, which is passing through P, sorry, when it is passing through P, we can see that if this is a tangent line, of course we know that when you are discussing concavity and convexity, if it's a concave function, the graph of the function would be lying completely below the tangent, isn't it? Now in the case of a convex function, the graph of the function would be lying completely above the tangent line. Now when you are taking the point P and when you are drawing the tangent line passing through point P, we can say that to the left of P we have a concave function, because the function is concave because the graph of the function is lying completely below the tangent, while to the right of P the graph of the function is lying completely above the tangent. So the curvature has got changed from concavity to convexity, and this function y0b, this graph of the function is crossing through this point P, it is cutting the tangent line. Similarly, when you take this function, that is graph or curve x0c, and similarly when you draw the tangent line, that is when you draw the tangent line that is passing through P, this is how it looks like. So which means that to the left of P, that is the graph of the function is lying completely below tangent line, but to the right of P, the graph of the function is lying completely above the tangent line. So from this it is very obvious that here to the left of P it was concave curve, and the curve becomes convex to the right of P. So this is of course this inflection point, and so it is this point we can see that the curvature is getting changed from concavity to convexity. And in the case of two curves, that is in the case of curve y0b as well as in the case of curve x0c, and we can observe that the third order condition is violated, and not just that, these two are having the same signs, isn't it? That is, dou squared z by dou x squared is actually positive in this case, and dou squared z by dou y squared is also greater than 0 or positive in this case. So we can say that P, it's actually representing an inflection point. Okay, so that is what we can observe in the case of inflection point. I hope this is clear to you, students. Thank you.